Okay, hopefully everyone can see that. Mr. President, members of the CCT, thank you very much for inviting me to give this talk. I discussed this with Dolores, and in fact, there's actually not really a Euramet perspective, but just because there's an NPL project related to the realising the redefined Kelvin, we thought that would be sufficient to encompass a Euramet perspective on the activities, because a lot of NIs are involved in this project. So these are the sort of things that I want to speak about. Let me just move the pictures out of the way. Yeah. These are the things I want to speak about. I want to just give a few words of the context about why and how we came to the actual project itself, the work itself that we're doing through the recommendation of the CCT in 2017, and also looking at the strategy. I also want to speak about the regulatory role that the mise en pratique has as well. And just those things combined really move towards what we proposed to do or are doing in the Euramet region in the period really now till about 2023 or so. And you'll see at the end, I've got a few questions arising from that, which are sort of quite general questions to the CCT as well, which we need to consider. So you'll be familiar with the wording of recommendation T1, which was in 2017. Of course, the first part of that was concerning the Boltzmann constant, but the second part is really concerning thermodynamic thermometry. And really, of course, the part concerning the redefinition, fixing the value of the Boltzmann constant, adopting the redefinition is all completed. That part is complete. But the second part of the recommendation, that member state NMIs take full advantage of the opportunities for the realization and dissemination of thermodynamic temperature afforded by the Kelvin redefinition, and the mise en pratique for the definition of the Kelvin, that has actually only really just started and will continue for probably a decade or more to come. I also had a look at we've also taken cognizance of the CTS strategy, and this is just some wording from the future scans 2023 to 2027, so really looking out beyond even the next CCT meeting. So in the section under definition of the Kelvin, it says that ITS 90 is kept up to date by incremental improvements of its realization and dissemination, and that also drove some of the things that we're doing in the Euramet region. That the requirements for any future temperature scale is to be reviewed in terms of stakeholder needs and cost of implementation. That's explicit in the CCT strategy, and that review is to be completed by 2027 before any discussions really held about implementation or introduction. And then, of course, and I'll come back to this, ensuring worldwide equivalence of temperature in the mixed situation we're going to get with T90 and T as well will become a key role for the CCT. And then the mise en pratique, this is also from the CCT strategy, some comments about the mise en pratique. It says a reasonable time interval, certainly beyond 2027, I'm quoting literally here, needs to be given for the mise en pratique and potential first iteration to be fully implemented, and the 2017 CCT recommendation concerning primary thermometry to be explored before substantive discussions concerning ITS XX are undertaken. So that's really just saying we're recognising the fact that the redefinition has happened, and we need to give space for primary thermometry to really flourish or explore as far as it can go before any future ITS is considered seriously. And then also we recognise that the possible use of mercury could be banned. Though personally I think it's unlikely for scientific purposes, but it could be banned, and that we should stimulate some research to look into appropriate alternatives if required. And the CCT is to develop an outline plan of how to keep ITS 90 functioning in the light of that eventuality. So notice again, not to put into practice the change, just to have something ready just in case that eventuality happens. So these were important considerations which we thought about as we thought about what should Euramet do in response to the Kelvin redefinition. That there was a recommendation which stimulated primary thermometry from the CCT, that the CCT strategy stimulated incremental developments for the ITS 90. It stimulated the thermometry community to get ready in case mercury fixed point was banned. It stimulated also the thought of reviewing stakeholder needs and cost of implementation before any consideration was given to ITS XX. Didn't anticipate any change in ITS 90 until after 27. And again, very important role for the CCT, that the worldwide equivalence of temperature in the mixed situation we have is a key role for the CCT, and it's going to get a bit more turbulent, I believe, in the years to come as well, and you'll see why in a few minutes' time. I want to say a few words also that we thought about as we came to approach a Euramet position and in the regulatory role of the mise en pratique. You're familiar with the contents of the mise en pratique. We're really looking at the areas which are for realization and dissemination of the temperature unit. And I suppose we were thinking, in 10 years' time, will everyone do whatever they think is right in terms of realizing temperature? Well, the answer is, of course, no. We won't realize our own scale. There may be independent NMI thermodynamic temperature realizations covering part of the ranges. That's certainly possible and certainly very likely, I think. But a mise en pratique will provide a very important framework for guiding and regulating that realization and dissemination. As I say, the CCT will have a key role in making sure that happens, and it'll be done, the regulation will occur to ensuring that appropriate key comparisons and secondary comparisons are done to ensure that there is comparability of measurements both within the regions and between the regions as well. And the working group for non-contact thermometry, we've already set up a CMC review protocol for direct and indirect primary radiometry at high temperatures to, in advance, get ready for this eventuality. So, let me just do that. So really that drove an evolutionary approach, I would say, to realizing the redefined Kelvin in our region. We're quite cautious, I think, in what we were trying to do. We drew together, we're very fortunate, or have been very fortunate in the Euramet region to have the NPL and EMRP programs to fund some of our activities. I proposed this project known as Realising the Redefined Kelvin, at which I was very fortunate to be funded, but it drew quite a range of national measurement institutes within Europe, both large and small, to focus on this common objective, which is really to begin to turn the Kelvin redefinition into a reality. It's a conservative, evolutionary approach to turn it into a reality, and that just gives the time frame of the project there, ending by the time of ITS 10. So here you can see the partners involved in the project, a good number of national measurement institutes, both large and small, also a good number of universities, both doing with measurement expertise, but also crucially with quantum chemistry modeling experience and expertise as well, and also some national measurement institutes who are outside the Euramet region, making key contributions to the work of the project as well. And there are four main activities of the activities that we're doing. One is realizing and disseminate thermodynamic temperature, so taking advantage of the redefined Kelvin above 1300 Kelvin. Our aim is to assign thermodynamic temperatures to iron carbon, palladium carbon, ruthenium carbon, and tungsten carbide carbon with very low uncertainties. We also want to establish the processes and procedures for the mise en pratique by indirect primary radiometry above really the copper freezing point, and really to get the processes in place to demonstrate a trial comparison that the thermodynamic approach using indirect primary radiometry is certainly capable of superseding ITS 90 above the silver point, really, by 2025. And I think we're on good track for that. And then realizing disseminate, again, thermodynamic temperature, not PLTS 2000, not ITS 90, between 0.9 millikelvin to around 25 Kelvin or so, though when you saw Patrick displayed in his last talk, we can certainly think you can extend primary thermometry to higher temperatures as well, certainly maybe approaching the water strip point even. But anyway, in this area, again, we're being a bit conservative and restricting our thoughts to that temperature area through practical primary thermometry based on Johnson noise approaches, Coulomb blockade approaches, and also gas-based, that is refractive index and acoustic type thermometry approaches, with at least the aim of potentially superseding or being in the position to supersede PLTS 2000 and the ITS 90 below the neon point by around 2025. I'm not going to speak about these very much, but these are two other things that are also involved in the project as well, extending the life of ITS 90. So you remember one of the discussions that were held in the CTS strategy about mercury and getting ready for mercury replacement. So we're investigating alternatives. There's been some very nice work done by Wes also and others looking at alternatives. And also looking at the impact of removing and not replacing the mercury point as well. Does that really make a huge difference? So we're going to have a look at that as well. And also looking at non-uniqueness of PRT calibrations to try and really understand that uncertainty and reduce it by at least 30% or so. And then the last thing, the last main thing that's in the project is facilitating full range primary thermometry, really gas-based primary thermometry. And key to doing this is some quantum chemistry, some quantum thermodynamic calculations, ab initio calculations, really calculating thermodynamic non-idealities of thermometric gases, the density and acoustic real coefficients of argon and of neon with very low uncertainties, and then we'll confirm them at a number of temperatures, the calculations, and then do some iteration to improve them even further, so that those numbers can then be used to actually do primary gas thermometry on a much more rapid basis than you can be done at the moment, to really get rid of the need of an isotherm type measurement and speeding up the use of gas thermometry. So that's exciting development, and there's been some really interesting progress in those ab initio calculations already. So I think I've said most of this. I want to speak now most of the rest of my talk about the high and the low temperature part. I said some things about this at the Beijing, which feels like a whole lifetime ago, considering what's happened. But first of all, realizing temperature above 1300 Kelvin, really above the silver point we're talking about here. We want to develop the practical procedures for realizing and disseminating it. So really putting the flesh on the bones of the meson pratique and the Kelvin redefinition above the silver point. We want to undertake a full-scale dissemination trial using high temperature fixed points to see how good it could be to disseminate the actual temperatures itself. And we're going to generate or develop a recommendation to CCT concerning disseminating thermodynamic temperature by indirect primary radiometry with very low, hopefully with very low uncertainties. Just to summarize really, so in the INC project, which we mentioned a while ago, really 6 years ago now, six years ago, we measured the thermodynamic temperatures of the cobalt, platinum, and rhenium carbon fixed points with very low temperatures. Here, by early or by spring 2022, we hope to have with similarly low uncertainties, iron, palladium, ruthenium, and tungsten carbide. And the aim is to really move away from the ITS 90, which has got obviously 3 defining fixed points at high temperatures, the silver, gold, and copper. Peter Saunders did a really nice paper looking at the non-uniqueness aspects of using 3 different fixed points. And we use, of course, Planck's law in ratio form to really move to something more flexible, where you have high temperature fixed points with known thermodynamic temperatures. You choose the 3 that you really want to use to realize the thermodynamic temperature in your own NMI. You can use a parameterized form of Planck's law to represent the signal of your pyrometer to do that. And then you can establish a low uncertainty thermodynamic temperature realization in your NMI using these fixed points. And we think you can do that with uncertainties comparable to or even lower than ITS 90. Then just moving to the other end of temperature, we want to realize and disseminate T, again from 0.9 millikelvin all the way to 25 Kelvin. You've seen that slide already. And here you can see there's a very convoluted mix of different ways of realizing and disseminating temperature. I'm not a low temperature measurement specialist, but I'm sure Christoph or Luan or others can speak much more eloquently, or Patrick, about this than I can. but it's quite a jumbled mix of different approaches. There's an overlap, which we heard about earlier, some nice measurements that were done by Eleni Kanam confirming the PTB work in the overlap PLTS region. But there's at least 4 different ways of realizing the ITS 90 in different parts of the scale, but up to 25 Kelvin or so, leading to different forms of non-uniqueness. And actually, these are very hardly realized in any institute at all. So one of the aims of the RealK project activities is to really do prime methometry by Johnson noise. That's PM prime, the MFFT, magnetic field fluctuation thermometer, is really a Johnson noise thermometer, up to around 5 Kelvin, and then use a more conventional refractive index or fast acoustic gas of 5 Kelvin or so. And then Coulomb blockade could act as some form of maybe secondary or eventually maybe primary device to bridge the two. But the key ones would be the Johnson noise and the acoustic or the refractive index approaches for doing T. So in summary, really, by the end of the activity, we hope to have done high temperature dissemination, realized and dissemination trialed with recommendation to CCT for parallel running of ITS 90 and T. Though I do believe that ITS 90 will increasingly wither over time because the low uncertainties that are attainable and the more robustness that we have by just using indirect primary radiometry. To put in place the dissemination processes for less than 25 Kelvin and the facilities in place as well, with recommendations again concerning ITS 90, PLTS 2000 and T to CCT by April 2023. We'll have done the ITS 90 life extension. We'll hopefully have got the essential gas-based thermophysical properties calculated by ab initio approaches with those low uncertainties. And then when we have that, I would see that there's going to be an expansion, and again, Patrick spoke about the possibility of that already in his talk last time, of extending it to higher temperatures above 25 Kelvin. But maybe just a few things we should think about as CCT as I come to the end of my talk. One is, of course, in the longer term, we need to think about, why do we need to anchor traceability in the National Measurement Institute? If you actually have practical primary thermometry, which you can then implement in industrial or other processes, you have then direct linkage to the Kelvin actually in the process itself. And how do you govern that aspect? I'll ask that question again later. Of course, there's sensor self-validation. That's really having things like fixed points built into sensors to do validation at particular temperatures. That's one aspect, one way of doing it. That's like an intermediate step. Some of the photonic thermometry in the longer term might come along to provide temperature traceability at least in restricted temperature ranges with competitive uncertainties. It has a way to go yet. But of course, I think that there will be practical primary thermometers that can be used in real world situations. Johnson noise may be one of them. Acoustic thermometers certainly will be used, I think, for realizing and disseminating T in NMIs, but maybe over the long term, maybe elsewhere. Even Doppler broadening thermometers, small scale, those Doppler broadening thermometers may be become useful as well. Who knows? So these are some things for us to think about, or I think the CCT will have to think about as this situation evolves in the coming decade, really, in this decade. I think, again, picking up on the point that was in the strategy, are there any newly identified significant user needs driving a need for a new temperature scale? I asking the question we asked in 2017, is ITS 90 seriously deficient from any user point of view? Personally, I think the answer is no, but maybe people know of a significant user that needs better than ITS 90 and that can't be served by T minus T90, for instance. So the question is, will ITS 20XX ever be needed? Well, that's an interesting question, which will be an answer in the later part of the decade. And similarly, will defined temperature scales ever be supplanted or fully supplanted by thermodynamic methods? It's a moot point yet. You may still need to have a defined scale in the central part of the temperature range. Are we ready if the mercury fixed point was banned, and what impact does that have on the ITS 90? I'm not sure we've really if we are really ready. I'm not sure if you've really answered that question yet. How do we, I don't think this question's even been answered yet either. How do we regulate the temperature dissemination in this ITS 90 and PLTS 2000 situation? How do we regulate that? And then when practical primary thermometers become available, maybe even as soon as 2025, but certainly by 2030, how do we view those in terms of providing traceability? How do we validate them, or do they need validating? So these are very interesting questions for the CCT to consider. So that's really the end of my presentation. I've given a bit of context as where we started from in the Euramet region, and about the strategy, the recommendation, the role of the mise en pratique, and how that drove evolutionary way of thinking in terms of realizing the redefined Kelvin. The Real K project, which is really the embodiment of those thinkings, is really all about establishing T above 1300 Kelvin, establishing T below 25 Kelvin, making sure that the life of ITS 90 is extended so that it's fit for purpose, at least for this decade, and preparing for growing acoustic gas-based and maybe other types of primary thermometry in the central belt of temperature, certainly from the water triple point upwards. It's going to be a rise in practical primary thermometry, no doubt, as well. And that's going to cause some interesting questions for us as CCT. And with that, I finished my talk. Thank you very much for your attention.